So I will record all of our lectures in case you have technology issues and you have to drop off and or you're sick or whatever. You can always watch them later on Canvas. But I always encourage you to attend if you can, because sometimes my computer doesn't work. I had my power go out last summer session and I lost some of the recording. Anyway, so let's get started. We have quite a bit to get through today. So this is ESS 15, Global Climate Change. We're going to be talking about our climate system, how climate changes, why it's changing now, how it's changed in the past. Okay, and you're probably interested in that if you're taking this class. So we will get into all of that information. So a little bit about me. I recognize some names, so I know there's a few people here from summer session 1. I taught the 2 previous ESS classes last summer session, but just a little recap here. Reminder, I guess, is that our class will be held from 1:30 to 3:50. So on paper it says 1 to 3:50, but I'm giving you about 30 minutes each lecture back to kind of do some independent, what I'm calling pre-work, just because it's just too long for us to be together and me lecturing and us all sitting on a computer staring at Zoom. So each 30 minutes, kind of from 1 to 1:30 is what I'm allotting. You can do that pre-work whenever is more convenient for you. All the lectures will be live through Zoom as long as I don't have any issues. I think there'll be one lecture that I'm going to be traveling, so I'm probably just will pre-record that and then you can watch it on your own time. So you can call me Dr. Nice, Dr. Mindy, Professor Nice, Mindy. I really don't care. My pronouns are she and her. Fun fact, you may see my face on some of the buses on campus. I graduated from UC Irvine in 2019 with my PhD in Earth System Science, and they did this whole spiel, and so there's a bunch of pictures of me floating around campus. Okay, so just a little bit about me. I am married. I have a son named Milo who is actually sleeping in the room right next to me. He'll wake up and I will deal with that when that happens. I have 3 cats and obviously my husband here. We like traveling and doing cool things. I really like this picture here in the middle. This is us when we were in France, in Paris. We stopped by Mary Curie's lab to check out that, which was really cool. As mentioned, I graduated from UCI in 2019. I've taught 8 of these real-time remote courses so far, so I think I understand what I'm doing, but I'm always welcoming feedback. If there's something that could be done differently, please let me know. I'm trying my best to be flexible. I know people are on different time zones, but I think these courses are best taught more live than you just listening to me later on, because then you can actually ask questions real time. Okay, our TA for this summer session is Chris McGuire. There he is. Chris, do you want to introduce yourself?
Yeah, definitely. Hi, everybody. Excited to be working with you for this summer session too. Like Mindy said, my name is Chris McGuire. I'm currently a 5th year in ESS, working under Professor Crook, Dr. Crook rather. And I'm hoping to finish up. So in a month, I will be defending. So this is my last class, but I'm here for you. So if you need anything, feel free to reach out and email me. It's going to be pretty fast paced. We're going to cover a lot of stuff. So I want to make sure that you understand everything thoroughly. But yeah, shoot me an email if you have questions. Thanks, Mindy.
Yeah, thanks, Chris. So yeah, Chris's resource, I'm your resource, and we will help you get through this. Okay, so the first thing I want to do is let's tour Canvas. One of the things that I find is some people just don't know where to look for things. So I'm giving you this time now. I will show you where I will put the recordings, and I'm going to show you where to find important documents. So we're going to go to Canvas right now, and you can follow along with me. This is what you see when you get to the Canvas page for this class. Okay, it should say ESS 15. On the front page, this is going to have really all of the important information. So if you're confused about something, this is the syllabus basically on this first page. Of course, if you would like, you can download the PDF version of the syllabus, but it's all written out here as well. So here is the first page. I will get to this assignment extension request in a second, but we'll just move through. Here is my email. Here is, right now I have office hours set on Mondays because Mondays are going to be your due dates for your quizzes and your homeworks. So I'm assuming that's probably going to be when you have most of your questions. And if that's not working out, we can look at it when the time comes, but I think Mondays will be best. And oops, I forgot to add the Zoom meeting link here. I'll do that. There's Chris's email and contact. And just, yes, another reminder, this is a fast-paced class, okay? If you took summer session 1 already, you know it goes fast. That's out of my control. These are 5 weeks. We're cramming pretty much all the same material in half the time. So it's going to be long. There's going to be a lot of stuff. I'm going to do my best to get through that with some excitement, but there will be days where it's a little boring and there's nothing I can do, okay? Here's your learning outcomes, what I hope you get out of this course. Important dates, please mark these on your calendar now. Obviously today, first day of class. The final project, there is no final exam in this class. Rather, you're going to complete a project and review each other's projects. Not everyone's, that would just be a little mean of me to make you review 50 other projects. But you will do that submission and peer engagement on Tuesday, September 12th, which is what would have been a final exam day. Okay, and I'll talk more about that in a second. Your grades will be available to you via your transcripts on September 21st. I'll have your grades submitted well before then, and you'll see those on Canvas. Okay, how will you earn your grade in this class? 7% is going to come from Zoom polling or participation. So one of the reasons why I really like you to come to the live lecture is we will be doing questions, engagement activities to try to help you understand some of the more complicated or complex mathematical things that we just have to get through in this class. And those are worth 7%. You do not have to check in. You do not have to answer the questions correctly. And you don't have to answer all of them. I'm just looking to make sure that you were there for most of the questions, okay? So if you step away to go to the bathroom or your Zoom logs out, don't worry, okay? I will see that you answered a few and you get participation for that day. Daily check-ins. So after each lecture every day, I have an online survey. It's through Canvas. And it's just going to be kind of a way to recap some of the information that you just were presented. Okay, and this is actually a scientifically proven way to help you retain information by decompressing and letting some of that information flow out. And the daily check-ins will be different each day. Some days it'll be, spend a minute writing down everything you learned today. And some will be more like, hey, pretend you're the professor and write some questions, some exam questions. Okay, and this also helps you process the big picture information. These are graded on completeness, not correctness. Okay, I'm just going to go through to make sure you completed them and you get some points there. There are 5 homework assignments, I believe, or was it 4? 4 homework assignments, and those are going to be worth quite a bit. And this is where you're going to do a lot more of the math requirement for this course will be in those homeworks. And you'll have weekly quizzes. There's 5 of them. So each one is worth quite a bit. You get 2 attempts at each of the quizzes. They're not timed. And your lowest quiz grade will be dropped at the end of the semester or quarter summer session. And then your final project is worth 15%. Okay. There is no textbook for this class. Instead, I encourage you to look at some of the open access resources available that are free. For example, here, this Introduction to Climate Science, some of the IPCC or Intergovernmental Panel for Climate Change's policies and documents. We'll be looking at those quite a bit, and those are all available here. And also, I just recommend Googling what you're curious about. The Wikipedia pages, especially when it relates to different climate change topics, are pretty thorough, and you can always find their references at the bottom to take you on to further research. Okay, so again, participation, you only need to be present for 70% of the lectures to get full points here, or 7 out of 10. Yes, your homework here, there's going to be 4 homework assignments. A big thing that I faced with last summer session is students turning in answers from ChatGPT. Now, I'm not going to say you can never use ChatGPT because I would be a hypocrite. I've actually used ChatGPT to help me write my resume because sometimes I struggle with action verbs. And so I use ChatGPT to help me come up with sentences or come up with verbs. I use that information and then I summarize it or I interpret it into my own words. You can do that. But if I see or Chris sees that you are copying and pasting ChatGPT into your homeworks, you're going to get a 0 and I'm going to report you because that is cheating. That is using something else's knowledge and claiming it to be your own. I know it's a weird territory we're in, this AI, but we need to set a precedent that using that it's not helping you if you're just copying and pasting, okay? So please just, you can use it to help you understand better, but make sure you're interpreting that information into your own words. Okay, your quizzes will be mini exams. They're going to cover a week's worth of material, which when you do the math is about 20% of a normal quarter. So there's a lot of information. So treat them as mini exams. They must be completed by Mondays at midnight Pacific time. Okay, so I suggest you a lot about 1 to 2 hours to take those quizzes because there's maybe probably about 40 questions or so on each one. They're all a little different. The quizzes are open book, open note, meaning you can use our lectures, you can use the lecture notes, you can use your homeworks. But they're not open peer and they're not open Google, meaning please don't, text each other, or we might get a Discord channel. Last summer session, we had a Discord channel. If you guys want to set that up, you can. I'll post the link. But don't confer with others for the quizzes. Okay, final project. I'm not going to talk too much about this today, just because I don't want to overwhelm you with that information. I will talk about the final project probably on Thursday, but a few of you have already started looking at that. So go ahead and take a moment to look at what the final project is about, and then I will go into more detail about that on Thursday. Okay, last thing I want to address on Canvas is this assignment extension request. Okay, I know life happens, things come up. It is really difficult as an instructor, as a professor, I want you to learn, I want you to do the work. And I know many of you are eager. If something comes up, you're like, I want to do it, can I have an extension? And I understand that. But because this is such a fast-paced course, I'm trying to get feedback to you all quickly, meaning after the quiz is due, I want to go through and see which questions you struggled with and help you, record a video going over those questions. And if I'm extending assignments continuously for many people, I can't do that. Okay, and so this is what I'm implementing this summer session, which is you get 1 free extension on either a homework or a quiz up to 3 days past the original due date. Okay, that means if it's due Monday, you have Tuesday, Wednesday, you can turn it in by Thursday evening. Okay, the caveat here is that you need to submit this request to me before the due date. So that means be proactive and think, oh, I have travel coming up, or I have something coming up. Maybe I'm going to need that. And you can always turn the assignment in on time, right? But this is your request here. You'll submit this survey, it'll alert me, and I can grant you that extension. But otherwise, with extensions in a 5-week long course, it just gets really, really tricky. Okay, so always please reach out to me or Chris if you have any questions or if something's coming up. We can help you now. We cannot help you after the final if you didn't turn things in. Okay, any questions, comments? All right, so that is the Canvas tour. So let's get into some stuff, some science. So I hope many of you were able to do some of the pre-work today. And I will sometimes bring in the pre-work into the lecture, so that's why I would like you to make sure you're doing it beforehand. And one of the assignments today for pre-work was taking this short Sixth America survey and figuring out where you fall in your feelings about climate change. Okay, so I'm going to launch this poll here, and this is how Zoom polling works. It should pop up a box on your screen, and then you can submit your answer. Your answer is anonymous, although at the end of the day, I can see who checked in for each question. And then we'll talk about it. All right, so here we go. Yes, so right now of our class, we have 50% of you that are alarmed and 37% of you are concerned. I'm just going to take a screenshot of this because I'm going to come back to this at the end, and I just want to see if any of our ideas or thoughts have changed. So let me just save this really quick. All righty. So when we look at Six Americas, this is this Yale program on climate change. They've been doing these surveys and this polling of America and our viewpoints and our thoughts on climate change for many years now. It's been over 10 years. And we can see that the alarmed category has been increasing. So the last issuance of this data was December 2022. And so when we look at America, about 26% of Americans are alarmed, which is a little bit less than our class, but that's because I think there's also a demographic difference. Many of you are younger compared to the average American. And then we look at concerned, 27%, and we can see a lot of change through time. Does anyone want to make a guess as to why, and you can put your answer in chat, why we have some of these variabilities, these ups and downs in the percent of Americans that fall in each of these categories through time? What do we think? Yeah. So a lot of this has to do with, yes, absolutely great answers here. Natural disasters, like what just happened recently, right? Humans are not good at remembering events and experiences from a while back. We're always really interested and keen on what's happening now, right? What's happening now, right, is we have historic heat waves and, flooding. And so that kind of triggers people whenever they take these surveys, like what's recently happened. Also, yes, the effects are beginning to be realized by many people, and that's maybe why the cautious and concerned rates are changing. One thing that really is impacting these numbers, especially these big peaks and dips here, is politics. Okay, so in this class, I'm never going to tell you who you should vote for or what political affiliation you should have, but I'm going to tell you the science and allow you to make informed decisions. And what we can see here is that after big elections, say 2018 and 2016, and things along those lines, we do see big shifts in what's happening in terms of some of these opinions. Okay, so we'll come back to these later on and see how we do. But what I want to do right now is actually look at some of the data. How do we in our group, our demographic group, compare to the majority of Americans? So our first question, yeah, exactly, is global warming happening? And these are just yes or no. And these are the surveys that the Yale Climate Group sends out. All right, so here we go. 97% of you are saying, yes, it's happening. When we compare that to the Americas here, right now, 72% of Americans, this is in 2021, this is their most recent big survey they did, show say yes, that global warming is happening. What's really cool about these surveys is that you can actually go to county level. So you can see the darker reds here, especially say in Orange County and other places along the coast of the West Coast here, have a higher polling rate. But on average, if you take everyone together, we're looking at about 72%. So our class right now is even higher, we're at 97%. Now my second question here is global warming caused by human activity? Okay, I'm not sure what's going on with my camera. And to answer your question, yes, they're on Canvas under files. Okay, I'm just gonna, there we go. Okay, so is global warming caused by human activities? Our class says 95% yes. We look at America, only 57% of American adults in 2021 said yes, that this is being caused by human activity. Okay, so again, our demographics are different. And so, yeah, okay, we're gonna continue on here. What about this question? Do most climate scientists think global warming is happening? Okay, so here on our class, we're saying 95% say yes. When we look at the American adults, 57% say yes. So the most recent analysis for this number is actually over 99%. Over 99% of publishing, actively researching climate scientists do believe global warming right now is happening. Okay, so my next question is, have you personally experienced the effects of global warming? Okay, sorry, I don't know what is going on with my camera. It's really driving me a little bonkers. Okay, so you personally, 83% of you have experienced the effects of global warming. When we look at America, now we're starting to see our numbers decline. So 46% of American adults say they've personally experienced the effects of global warming. Okay, so you can start to see now there's this dissonance where we think we know it's happening, but because maybe I haven't personally experienced it, I'm not as concerned or not as engaged with it. Okay, so we'll see a little bit about that here. Are you worried about global warming? Yes or no? All right. So here, 89% are saying yes. When we look at the whole America here, about 65% of American adults are worried. Okay, and of course, these surveys are very just yes or no, right? Not like a level of worry. But this is also interesting that we may not have experienced some of the impacts, but we're still concerned or worried about the change. Okay, what about this one? global warming will harm future generations? Yes or no? Okay, so here we have 95% of you saying yes, and about 71% of American adults are saying yes as well. So interesting, it's not affected me. And again, I'm saying this as a general, right? So the American adults mostly haven't experienced the change, they think, but they are worried about the future harm. Some questions about policies. Should we fund research into renewable energies? All righty, so 92% of you say yes, and now we're starting to see some really red on our map. So 77% of Americans want to see more funding into renewables. Should we regulate carbon dioxide, CO2, as a pollutant? Yes or no? All right. So here I have 91% of you saying yes. And again, 72%, a high percentage of Americans say that we should do that. I'll let you know that recently the Supreme Court actually ruled that the EPA, the Environmental Protection Agency, was not allowed to regulate CO2 as a pollutant on existing power plants. So that has limited our federal government's ability to try to reduce some of this pollution, but we'll talk about some of these policies towards the end of the class. And the last one, do you discuss global warming at least occasionally? All right. So our number has dropped to 64% saying yes. It's still quite high compared to the whole America. So when we look at this number, we see there is a concern for climate change or global warming. We're somewhat concerned of future generations. We want to invest in renewable energies, but only about a third of Americans talk about global warming occasionally. And so this is where our problem lies in terms of initiating more change, is that we don't talk about it enough. So hopefully by the end of this class, you are more confident in discussing climate change and global warming and engage more on these topics because they're very important. We can't just ignore this problem, so we have to tackle it head on. And in this class, we're going to be talking a lot about human-caused climate change. And so I just want to set the precedent here that the scientific consensus is that humans are causing the recent changes in our climate system. And so I want to read to you this statement from the Summary for Policymakers Climate Change Synthesis Report. It says, it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. Okay, so when we talk about anthropogenic climate change, we're talking about human-caused climate change, mainly through the burning and use of fossil fuels that have released carbon to our atmosphere. And that carbon is going to impact our planetary temperature. And so if you are unsure or you want to talk more about this, happy to do so. But I am teaching this class with this consensus that human activity now is the main cause of the climate change we're seeing. Okay, so we are in our great experiment. We are seeing changes to our planet that we've never seen before in human history, and we've never seen before humans came about, through looking at some of our records that we have, these climate records. And so I want us to get very familiar with this graph. This is showing the amount of carbon dioxide, CO2, in our atmosphere measured over Hawaii, specifically Mauna Loa. And what you'll notice is on the x-axis, we have time or year. So this data set or this record starts in 1958, and it is continuous all the way to present day. They're making measurements today as we speak. On the left axis, we're looking at CO2 mole fraction, which is basically how many molecules of CO2 there are per the rest of the air sample. Okay, and right now, CO2 is in our atmosphere in parts per million level, which means that for every million molecules of air, there's about 420 molecules of CO2. So it's a very small amount, but this gas, this compound, is really, really important in regulating our climate system. And so we'll talk about this greenhouse effect. Just for reference, when we look at the amount of CO2 in our atmosphere and we look at a rate of change or how much CO2 has changed over a year, here is the June 2023 value of 423.68 parts per million. Last year, June 2022, was 420.99 parts per million. So we're seeing a change of almost 3 parts per million per year. That might not seem like a lot, but after we do some of our labs or our homeworks, we'll see just how much CO2 has changed before humans came about. And this number will then be very shocking because it's very fast. Okay, so one of the things I really hope that you get out of this course is how to read scientific graphs, how to read scientific figures. And so what I want us to do for, I don't know, maybe like 3 or 4 minutes, is I'm going to break you into breakout groups. And I want you, well, no, let's not do that, because when I break you into groups, you can't see this screen. We'll just do it here together. I want you to look at this graph here, and I want you to tell me what we're looking at. What is this figure showing us? So let's look at our title. Let's look at our axes labels, any descriptors that we see on this graph. And then I want us to think about what scientific interpretations we can make with this figure. What can I, as a scientist, conclude from this data or this figure? Okay, so take a few minutes, look at it, and go ahead and type what you think into chat, but don't hit submit yet. I want us to hit submit all at the same time. So take about 2 minutes. All right, so you can go ahead and start submitting what you think in the chat, and we're going to discuss it as a class here. Okay, awesome. Right, right. Whew. Great. So when we look at these graphs, and I want to pause here and say this figure is from the IPCC, or the Intergovernmental Panel for Climate Change's assessment report. And most of the figures I will show you are from that report. And what they show is what most of you have said here, is that if we look at the annual average temperature from 1850 through, I think this would be 2010 or so, we can see that temperatures are increasing quite a bit. And then when we look at the decadal average, meaning you take the 10-year average and plot that, you can see how each decade in the past 40 years has actually is getting warmer. And these are an anomaly, which means we take a period of time, in this case, 1961 through 1990, we average the global temperature for that 30-year period, and then we compare every year to that average. Okay, so that's what we mean by anomaly. And yes, you're right, every year is getting warmer, and every decade is getting warmer too. Okay, so this is our surface and land, or ocean and land, excuse me, temperatures data set. All right, so we're going to talk about all of these different components of our climate system, and we're going to start really with our atmosphere. What is in our atmosphere? How does this impact temperature? Okay, I will be right back. Give me like 1 minute. I have to go do something really quick. So just take a quick little refreshment break. Okay, I am back. Sorry about that. That will probably happen a few times. The baby woke up from his nap too early, but he's back to sleep, so we're good. Okay, so we're going to talk about our atmosphere today and lead us into this idea of our climate system. Okay, so we'll see these learning outcomes on every lecture, and these are really great ways to summarize the information that we'll learn that lecture, right? So today we'll talk about some of the links within our Earth system. We'll talk about weather versus climate. We're going to talk about our electromagnetic spectrum, what determines what radiation is emitted by different objects. We'll talk about the difference between short and long wave radiation, and that will lead us into the impacts on our planet. Okay, so what is climate? When we talk about the climate system, how is the climate different from weather? Okay, climate is the weather over a certain period of time in a specific region. Okay, so when we think about the climate of Southern California, the climate of Southern California is what's called a Mediterranean climate. It has hot summers and cool, wet winters. Okay, and we can see here our Köppen climate types in the US that there are many different climate zones, even just in the United States. And when we think about climate, usually we're talking about a 30-year period. So we look at all of the weather over, say, Southern California for 30 years, and then we can see, you know, what is the average temperature? What is the average rainfall? That's the climate. Weather, on the other hand, is the state of our atmosphere at any given time and place. Okay, so that's things like temperature, air pressure, humidity, whether or not it's cloudy and raining, is it super windy? And weather is what you get on any single day, but climate is what you expect, right? So you know what to kind of expect in terms of the climate of Southern California, but on any day you could get, a rainstorm, for example. So when we think about climate, we're talking about long-term changes. So I have a little video here to demonstrate this idea of weather versus climate.
Long-term predictions about the climate. How come we're so lousy about predicting the weather? Besides, this year, we had a colder winter in my town. For all the scientists know, we could be in for global cooling. Here's the difference between weather and climate. Weather is what the atmosphere does in the short term, hour to hour, day to day. Weather is chaotic, which means that even a microscopic disturbance can lead to large-scale changes. That's why those 10-day weather forecasts are useless. A butterfly flaps its wings in Bali, and 6 weeks later, your outdoor wedding in Maine is ruined. Climate is the long-term average of the weather over a number of years. It's shaped by global forces that alter the energy balance in the atmosphere, such as changes in the sun, tilt of the Earth's axis, the amount of sunlight the Earth reflects back to space, and the concentration of greenhouse gases in the air. A change in any of them affects the climate in ways that are broadly predictable. My friend's meandering represents the short-term fluctuations. That's weather. It's almost impossible to predict what will attract his interest next. But not hard to know what the range of his meandering will be, because I'm holding him on a leash. We can't observe climate directly. All we see is the weather. The average weather over the course of years reveals a pattern. I represent that long-term trend, which is climate. Keep your eye on the man, not the dog. Weather is hard to predict, like my friend here, but climate is predictable. Climate has changed many times in the long history of the Earth, but always in response to a global force. The strongest force driving climate change right now is the increasing CO2 from the burning of fossil fuels, which is trapping more heat from the sun. All that additional energy has to go somewhere. Some of it warms the air. Most of it ends up in the oceans. All over the world, the oceans are getting warmer.
Moderate to severe.
All right, so watch the human, not the dog. And that is what is happening. When we think about climate and climate changes, we're going to look at the long-term trend, not that some years are maybe a little cooler or just a little warmer, the whole long-term trend. So how and why does Earth have the climate that it does? Earth's climate is driven by energy from the sun. So in order to understand our climate, we must first understand our sun and how much heat or energy the Earth is able to obtain from the sun. All right, so let's think about radiation. Let's think about this concept of radiation. What emits radiation? Is it a plant, your computer, your cell phone, the engine of a car, or all of the above? All right. So the answer here is, in fact, all the above. Anything that has a temperature will be giving off radiation. The type and the amount of radiation that that object gives off is determined by its temperature. And I want to pause here and emphasize that the term radiation might have a negative or scary connotation, right? We think of radioactivity sometimes when we think of radiation, but in this, we're really just referring to the energy that gets transmitted through a space or without having to touch an object. Okay, and so we're not referring to specifically a specific type of radiation necessarily. Okay, so everything emits radiation, and our radiation consists of electromagnetic waves, right? So the molecules are moving in this wave-like pattern. And each type of radiation, and I'll show you our spectrum on the next slide, either visible light, radio waves, X-rays, gamma rays, they all have a specific wavelength or a range of wavelengths, and they all will move at the speed of light. And when I talk about wavelengths, I'm talking about the distance between the crest or the troughs. Okay, so here in this example, wavelength is sometimes denoted as the Greek letter lambda, and it's the physical distance between the peak here and the next peak. You can also do the trough. It could be this trough here and the next trough, but it's the distance between those features, and we can measure it. And so sometimes we refer to radiation as either having a short wavelength or a longer wavelength. It looks something like this. So I'm going to ask you right now, which one of these, A or B, has a shorter wavelength? All right. So yes, example here on the left, A, has the shorter wavelength. If we were to bring out a ruler or a tape measure and measure the distance between the peak here and the peak here, it would be shorter than the distance between the peak on B and the next peak. Okay, so A is what we would consider short wavelength or short wave radiation, and B would be longer wavelength or long wave radiation. Okay, this matters because the amount of energy that radiation has with it is dependent upon its wavelength. Okay, so the higher the energy, the shorter the wavelength. The lower the energy, the longer the wavelength. Okay, so high energy, short wavelength, low energy, long wavelength. Thinking about our sun and our Earth, which one of these objects has higher energy or more energy? Is it the sun or the Earth? Right, the sun. Okay, the sun has more energy. It's pretty hot, gives off a lot of heat energy and many other forms of energy that we're going to talk about compared to the Earth. And therefore, the main radiation that the sun is going to give off compared to that of Earth, it will be different wavelengths. And so I want to introduce us to this electromagnetic spectrum. So radiation is emitted by an object across a spectrum. Okay, there's no defined endpoints. It's not broken up. It is a continuous spectrum. And within this spectrum, we as humans have broken up the radiation into different categories. So for example, the visible spectrum, the light that we see, falls into this narrow band on the spectrum of electromagnetic radiation. Okay, just a little bit. To the left of visible light on this spectrum, we have longer wavelength energies. So we have radio waves, microwaves, then we have infrared. Okay, and then to the right, we can start to see that those wavelengths are getting shorter, which means higher energy. We have ultraviolet, X-rays, and gamma rays. And the amount and the type of radiation that an object will be giving off is going to be dependent upon its temperature. And we'll see that here in a moment. So as I mentioned, it's a continuous spectrum, and we can actually partition those wavelengths into different bands. So about 40% of sun's energy is emitted at wavelengths longer than the visible band. Okay, so the visible band is what you and I can see. Our eyes have evolved to be able to see that wavelength. About 10% of the sun's energy is emitted at wavelengths shorter than the visible band. So the Earth is receiving a lot of energy, a lot of radiation from the sun in bands that we can't necessarily see, but matter. Okay, and again, the radiation that has different wavelengths are going to have different properties. So in this course, we're really concerned with shorter versus longer wavelength. And the intensity, the total amount of radiation that an object gives off, as well as the wavelength of radiation that's emitted from that object, depends really on its temperature only. So when we look at this magnetic spectrum here, and I apologize, this one has the shorter wavelengths on the left and the longer wavelengths on the right. Look at where X-rays fall on our spectrum. Why would we not want to get an X-ray every single day? Right. X-rays are on the shorter wavelength side of our spectrum. And shorter wavelength means more energy, and that higher energy can impact our cells in our body, right? That wavelength can penetrate through our skin. That's why it can see our bones. And so it's useful to help us inspect and get a visual image of our bones if we think we broke a bone or whatnot. But we do not want that high energy getting into our system too much, right? So it can disturb our smaller structures like our cells and can cause cancer. And gamma rays too. Gamma rays, which are emitted from radioactive materials, are really damaging. Okay, you can watch the show Chernobyl to learn a little bit about how radiation can impact humans. So I'm going to introduce this concept called a black body. A black body is a scientific kind of thought process. And this black body, this object, is going to absorb all light shined upon it. Okay, 100% absorption. And in return, that black body object is going to emit a spectrum of energy, of radiation, that depends upon its temperature. And this is a hypothetical scenario. There's actually no such thing as a pure black body. But we can use this idea to help us understand the type of radiation and the amount of radiation that different objects will give off. So let's look at this graph here. On the x-axis, we have wavelength, okay, in micrometers. All you need to know is that on the left side here, shorter wavelength. On the right, longer wavelength. The vertical axis is, in this case, spectral radiance, or it's just the total amount or the intensity of radiation given off. And each one of these curves here, for example, this blue curve of 5,000 Kelvin, tells us that an object that is 5,000 Kelvin, so very, very hot, will give off energy or radiation along this spectrum, meaning most of the energy is going to be emitted in the visible wavelengths. Some will be given off in the shorter UV or ultraviolet, and then quite a bit is going to be given off over here in the infrared. Okay, what we'll notice is that as we move down in temperature, as we get cooler in our object's temperature, we're going to see two things happen. One is that the total amount of energy the object gives off decreases. So an object will give off less energy, and the wavelength, the peak wavelength, where it gives off most of that energy, gets longer. Okay, so the 5,000 Kelvin, most of its energy is being given off, say, maybe at like 0.6 micrometers, but the 3,000 Kelvin line is more like 0.8, micrometers. So the total amount of energy is lower, and the wavelength of the peak, where most of the energy is being emitted, gets longer. And this is bringing this idea of black body radiation into fruition. And we can actually put all this into a mathematical equation, okay? And this is the Stefan-Boltzmann law, which says that the total radiation, luminosity, power, we can use these terms interchangeably here. The total radiative power, or I, is a function of that object's temperature. So I equals sigma, which is a constant, the Stefan-Boltzmann constant, times temperature to the 4th power. And so when we look at what I ends up being, it ends up being watts per meter squared. And I'll talk about that, what that means in a second. But when we look at this equation, because temperature is raised to the 4th power, it means that a star twice as hot as our sun will actually radiate 2 to the 4th power, or 16 times as much energy. Okay, because that temperature, T to the 4, it's not linear. Okay, so when we think about how we change temperature, even just a little bit, will have a big impact on the total amount of radiation given off. And we know that the wavelength of peak emission is going to be based on temperature as well. And it's this formula here, or this law, Wien's law. The wavelength of peak emission is lambda max, so max wavelength here, 2898 divided by T. And T, the temperature here, needs to be in Kelvin. Okay, so let's pause for a second and think about what is a watt. Watt is a watt, okay? It is a unit of power, and it's also sometimes you can use it as 1 joule per second. But to me, like thinking about our daily lives, where would you encounter a watt? Well, a light bulb, for example. These newer, more energy efficient light bulbs, they only use 43 watts of electricity. Okay, so it's a way that we think about power or that energy. And so when we think about the amount of power that an object gives off, we usually refer to it in watts per square meter. How much energy is that object giving off per square meter or surface area of that object? Okay, so we will use watts per meter squared quite a bit as we move forward. Okay. So we're going to practice with this, but I would like us to take a little break first. We will do some of this math once we get back. So let's meet back at 2:40, and we will do some of these problems together. So I'll see you at 2:40. Here, and practice with some of these equations. So first thing we're going to do here is I want us to calculate the sun's power, or how much energy in watts per meter squared the sun gives off. All right, and we can do that by just plugging in the temperature to our Stefan-Boltzmann law. So here we have I equals sigma T to the 4, and sigma is this constant, 5.67 times 10 to the minus 8 watts per square meter Kelvin to the 4th. And that number doesn't change because it's a constant. So I will have I equals 5.67 times 10 to the minus 8 watts per meters squared Kelvin to the 4th times my temperature, which was 6,000 to the 4th. All right, and I'm smart, but not that smart to be able to do that in my head. So I'm going to pull out my handy dandy calculator, also known as Google Calculator. And we're going to type that into the calculator. So 5.67 times 10 to the minus 8, that whole thing times 6,000 to the 4th power, and we're going to get a number like this. Okay, so we're going to get this value here, 7. I have to write it out in order to get it. So 7. Let me get this number here. 73 million watts per square meter. That's a lot of light bulbs per square meter. All right, and we can do the same for Earth. Okay, in this case, it's going to be I equals, again, 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th. And now temperature here is 300 Kelvin. Oh, no sig figs, please. We're not worried about that. Okay. In fact, a lot of times I'm just going to have you round to the nearest whole number. Yeah, great question, but no sig figs in this class, not important. Okay. So we can do the same calculation. Oops. Yes, I love Spice Girls. That's awesome. So here we go. We're going to do the same math, 5.67 times 10 to the minus 8, and that whole thing times 300, the temperature of Earth, raised to the 4th power, and we get about 459 or so watts per meter squared. Where'd my PowerPoint go? Okay, so about 459 watts per meter squared. So we can see how quickly the amount of power or luminosity or radiation an object gives off changes because of that temperature change, right? So huge difference between the amount between the sun and the Earth. Questions? All right. So now let's practice with Wien's law, which tells us the peak wavelengths, where most of those emissions are coming from, like what wavelength. Okay, and this equation, lambda max, is a little bit simpler. It's just this 2898 constant over temperature. And so we know temperature. So lambda max here is going to be 2898 divided by 6,000. And we're going to get a value in terms of micrometers. So 2898 divided by 6,000. Again, I'm going to bring up my calculator. 2898 divided by 6,000, and I get 0.48-ish micrometers. Okay, so why don't you all go ahead and calculate Earth's peak wavelength and go ahead and get that in chat when you have your answer. All right, fantastic. So 9.66 micrometers. All right. And that's about right, or real, I guess I should say. And so what we can see here is the difference in that peak wavelength of the majority of that radiation emitted. So the sun is much shorter wavelength than Earth, longer. And this is going to be really important for setting up our greenhouse effect. The fact that the majority, most of the energy or radiation that the sun is emitting is in the form of short waves, short wavelength, but Earth is more long wave. Okay? And so just by looking at some of these curves, these black body curves, we can get a sense of temperature differences between these different objects, okay? So just to reiterate, hotter black bodies will emit or have greater intensities, meaning they're emitting more energy. Their peak will be at a higher energy or shorter wavelength, like our sun. Overall, they'll emit more energy. That area under the curve or that integral will be larger. And also something great is sometimes the color of the light, if it's in the visible spectrum, can inform us about the temperature of that object. Because the blues and purples are shorter and the reds are longer in terms of wavelength. So here's my curve. So let's just think about this again. Which of these spectrums here, A, B, C, D, or E, is going to be emitted by the second hottest black body? So not the hottest black body, but the second hottest. Oops. All right. So our hottest black body is going to be curve A. Okay, so A is the hottest. And we know that because it's emitting at a shorter, the peak emission is at a shorter wavelength, and also it's emitting much more, right? Going back to the Stefan Boltzmann law, temperature to the fourth. So the second hottest is going to be, oops, I missed. Second hottest is going to be, B, okay? And I didn't bring this one into the polling, I missed it here. But if we look at the coldest black body is going to be curve E. Okay, so its peak emission is a longer wavelength, and overall, the total amount of radiation emitted is much smaller. All right, so here are those temperatures for your reference. And so why this matters for our Earth system and our climate system is that the energy that the sun gives off is much different than the energy the Earth gives off, okay? So we are going to refer to the sun's radiation or the sun's energy as shortwave, okay? Because it's much shorter in wavelength than that of Earth's, okay? Again, the temperature of the object determines its radiation spectrum. And because Earth is not nearly as hot as the sun, it is giving off most of its energy or radiation in the long wave spectrum. Okay, it's really in the infrared. If you think about the different categories of naming that we have created for our electromagnetic spectrum. Okay, so sun is short wave, the Earth is long wave. Pretty important. Okay, so if we look at the differences between the sun and Earth, so this is I like this graph here that shows the black body emission curves of the sun and Earth. Now the sun is scaled by a big factor here so that you can put them on the same graph. Otherwise, the sun is way off the scale here because the sun is just so much hotter and it's going to give off so much more energy. But what you'll notice is that there's only a little bit of wavelength here, a little bit of radiation where the sun and the earth overlap. Otherwise, the sun is giving off much more energy in that shorter wavelength and the earth in the longer. Okay. Right, and we can do some more practice here, but for time's sake, we'll just keep moving on here. But we could calculate the wavelength of any object, the peak emission based on temperature, okay? And we'll just skip that. Okay, but let's practice with this one because I really like this idea that color can tell us about temperature. All right, so which star A and star B, which is kind of referring to maybe a bluish one, which one is cooler in terms of temperature? All right. That's okay. So cooler would mean a longer wavelength. Okay, so the longer wavelength here, when we look at our visible spectrum with color, the longer wavelengths are going to be the reds. So star A is actually cooler. Not like cooler, but temperature-wise is not as warm. Okay, so we're going to recap here because this leads us into the next big topic of what controls our temperature, is that the Earth mainly emits long wave energy or radiation. However you want to refer to it, I will refer to radiation. I will refer to them interchangeably. So long wave energy. The sun emits mainly shortwave. Now the differences in those energies is what is important for shaping Earth's climate. So what can we do with this information? We know now those spectrums of radiation emitted by our objects, our sun and our earth. Now we can calculate how much of that energy the sun is emitting that earth is going to receive, because we know that the main heat source, the main way earth is heated is via the sun. So we can calculate Earth's global temperature. And so I'd like to pause here and think about what controls a planet's temperature. There are these 4 main categories. The first being the sun or the main star in that solar system's luminosity, right? How much energy is that sun or star giving off? And how far is the planet from that sun or star? And that together combined is what we call the solar constant. Every planet in any solar system, you could calculate that solar constant. So how far away you are and how much energy your star giving off. And the next 2, the atmosphere, what's in the air around our planet, the albedo, we'll talk about that. And then also, is there a greenhouse effect? What's happening to the outgoing radiation from the planet? As the Earth is sending out heat energy, what's happening? We'll talk about that too. So the actual temperature we feel is determined by whether or not there's an atmosphere on the planet, which is why when we look for exoplanets, we try to figure out if they have an atmosphere, because without an atmosphere, you're probably not likely to have much life. Because that atmosphere is important for keeping in some of that heat. Okay, so Our sun's luminosity or power is really consistent over time. It has increased on a billion-year timescale, and we'll look at that in our homework this week. And if you look at the total watts emitted, it's a lot. But Earth doesn't receive all of this, okay? Otherwise, it'd be way hotter than we are, okay? So the question we have to say is, well, how much of this does Earth receive? Well, how far away are we from our sun? The Earth's orbit is a bit elliptical. It's not a perfect circle, and it's not a perfect ellipse either. And it does change through time, and we'll talk about that when we talk about climate changes naturally. But what you'll see here is that there are different points in Earth's orbit where we're a little bit closer to the sun and a little bit further away, okay? So what you'll notice is that in January, Earth is actually closer to the sun by about 7%, 147 million kilometers distance versus 152 million kilometers. But in January, it's cold. I'm confused. What's happening? Why is it that it's cold in California, maybe, in January, yet we're closest to the sun at that same time? What are we not accounting for? Yeah. The tilt, okay? So what actually controls our seasons, right? The fact that in January, the season we experience in the Northern Hemisphere, where California is winter, is because the axial tilt is away from the sun, okay? And that is gonna impact our flux, okay? So flux is the amount of energy that passes through a perpendicular unit, or perpendicular, let me start over. The amount of energy that passes perpendicular through a unit surface area per time. The way I like to think about this is if we have a light bulb or a flashlight and we hold a piece of paper directly perpendicular, okay, at a 90-degree angle, we are gonna get a very small but brightly lit area on that piece of paper. Now, if I take that same light bulb and I just hold my piece of paper at a lower angle, it's the same amount of energy from the light, but now it's illuminating a much larger area, and therefore it's dimmer. So when we think about flux of these two pieces of paper, which paper is going to have the higher flux of energy? Is it A or B? All right. The way to think about flux is kind of how bright or how illuminated that area is, okay? So A is the answer here. A is gonna have the higher flux because we can make up a number. Let's say this is a 40-watt light bulb. And let's say that sunlit area is, I don't know, 1 meter squared. Obviously, that's an exaggeration. It can't be that big. It's a piece of paper, but just for math, 40 watts per meter squared is what we would end up with in terms of our flux. And let's say, again, same 40-watt light bulb here, but now this area that's lit, let's say it's twice the size, the square area. So it would be 40 divided by 2 meters squared, 40 watts divided by 2, which would be 20 watts per meter squared. So why am I talking about angles and flux? Well, we know our Earth is tilted. We just saw that. And so there are places on our Earth that are going to experience more of this spreading of energy. And that's going to control some of our temperature on our planet. And it also will determine how much energy we intercept from the sun, okay? So when we think about our sun, it is sending radiation or energy through all directions. It's a sphere, so it's sending it out in all directions. That big number of watts goes all around in a sphere. And the further this from the sun, that energy is spread over a larger and larger sphere. Okay, so we can see here that the radius or our distance from the Earth, from Earth to sun, is 1.5 times 10 to the 11 meters. And Mars is further. And so when we think about the solar flux, how much energy is Mars intercepting? It's going to be smaller than that of Earth. Okay, the amount of energy Mars gets is going to be smaller because that sphere, based on the radius or the distance to the sun, is bigger. And so that energy gets spread over a larger area. The denominator gets bigger in that equation. Okay. For this class, we're not going to worry about all the details and all the math here. But if we want to know how much, what is our solar constant? How much of that sunlight do we get on Earth? The solar flux density is the luminosity of your sun or your star divided by the area of the sphere. And the area of the sphere here includes a radius, and that radius is our distance to the sun. Okay, so you can do the math, do the calculation. For our class, I'm just going to give it to you. It is about 1,370 or 1,370 watts per meter squared. And that's our solar constant. And that is strictly due to how far away we are from the sun and how much energy or that luminosity power of our sun. Okay. Now, only half of the Earth, or about half of the Earth, is sunlit. Okay, because the other half is in darkness. And so if we want to actually get the amount of energy that's hitting the sunlit portion of Earth, we have to divide that solar constant from the previous slide by 4 because of this concept here that the amount of sun's energy intercepted by a spherical planet is the same that's blocked by a flat disk or circle. Okay, so you can see here's our sphere on top, but it's the same as a flat disk. So the area of a circle and the area of a sphere, there's this extra 4 multiplier. And so we just need to divide by 4. And that's going to give us the total energy that the sunlit portion of Earth gets. So we get about 342 watts per square meter in the sunlit portion of Earth. So every square meter in the sunlight gets 342 watts from the sun. All right. So what does that mean? Thinking in my analogy to a 40-watt light bulb, that's about having 9 of those 40-watt light bulbs per square meter of every meter squared of the sunlit portion. It's a lot of energy, okay? And that's why we have a temperature, because we're getting quite a bit of the sunlight. And that energy, that radiation, is going to heat up our planet. Okay. So we're going to continue to fill in what I'm going to call Earth's energy budget. Okay, when you think of a budget, you might think of money, right? I get so much money per month through income, through my job, and some of it goes immediately away, back to space, through my mortgage or my rent. Some goes over here, right? We're thinking of where is the energy going in the Earth system. So the incoming solar radiation is about 340 watts per square meter. And throughout the course, we're going to fill in the rest. Where is all the other energy going? Okay. So we know that the amount of energy coming from the sun is pretty constant, right? I told you that the sun's luminosity changes, but on billion-year timescales. And so the reason we experience day and night and seasons has to do with the other mechanics of Earth's orbit around the sun and our orientation towards the sun. Okay, so our revolution, okay, we revolve around the sun in our orbit once every 365.25 days. Okay, 0.25. That's why every 4 years we have a leap day or a leap year, right? We have to add that extra fourth of a day that we've kind of forgotten about every 4 years. And again, as I mentioned, there is a small difference in our orbital distance, but it only leads to really small influence on seasonal heating. Okay, it's not the main culprit or the main factor that determines our temperatures in the season. What determines our temperature is really our tilt, whether or not our hemisphere, and I'm gonna be Northern Hemisphere centric because we're in the Northern Hemisphere, most of us probably for this class, our Northern Hemisphere, is it tilted towards or away from the sun? And that's gonna determine our seasons, okay? Our rotation, the Earth also is rotating around on our axis. And our speed of rotation defines our day. So on Earth, our day is 24 hours. Other planets may revolve faster or slower, and then their days would be different in terms of length. And this is the reason we have day and night, because sometimes the Earth, our position on Earth's surface is tilted towards the sun or illuminated, and then as we rotate, we go into night. Tilt. Earth's axis today is tilted about 23.5 degrees. Okay, 23.5. And this tilt is the principal cause of our seasons, and it's going to affect the amount of energy from the sun that each location or each latitude really receives. It impacts our length of day, as well as that flux or that spreading out of energy, which we also refer to as solar angle or beam spreading. If you take the energy from the sun, the Earth is round, some of that energy will be spread over larger surface areas. Okay. Here, my sun, and this diagram is to the right. I'm going to draw it in. And in this case, the Northern Hemisphere is tilted towards the sun. So we're in summer in Northern Hemisphere in this image. Which location would have longer days? Would it be Texas or Alaska? All right. So in the hemispheric summer, so when I say that, I mean we're talking about the hemisphere that's in summer. And so in this case, the Northern Hemisphere is in summer. The pole will be experiencing 24 hours of daylight. And really anything above the Arctic Circle in this case will never see darkness because of the tilt. Even as we go throughout the day and revolve here, or sorry, rotate. Even as we go throughout the day and we rotate, that North Pole, anyone above the Arctic Circle, will be pointed towards the sun, even throughout the 24-hour rotation. And so this is why Alaska has longer days in the summer. In fact, some parts of Alaska will have 24 hours of sunlight. Okay, so the answer is B. Now in the winter time, oops. Now we're in winter. My diagram didn't change. This is still showing summer. But in the winter time, which location would have longer days, Alaska or Texas? All right. So the opposite is going to be true here. Now, again, my diagram didn't change. I think I have it. Let me see. Nope. In wintertime, our northern hemisphere would be tilted away from the sun here. And so the Arctic, even during the day as the Earth is rotating, would be always facing away from the sun. And so above the Arctic Circle, they experience 24 hours of darkness. So now you can start to see the latitude of our planet, where you are, how far away you are from the equator, north or south, is going to impact your seasonal range, right? The Arctic, Alaska goes from 24 hours of daylight down to 24 hours of darkness. And that is why it's super cold there. And we have glaciers and a lot of snow and permafrost. And we don't have that in Texas or near the tropics. So that, our tilt, impacting our seasons, impacts our length of day, how much total energy those latitudes receive, and will impact the climate zones across the planet. Okay? When we're orbiting the Earth, we have different periods where we're going to experience different amounts of sunlight in the hemispheres. We have our equinoxes. Equa meaning equal. There are 2 times a year where Earth's axis is neither tilted towards the sun or away. And this results in nearly equal amounts of daylight at all latitudes. Okay, so that's going to be in spring, in March, and in autumn, in September. The Earth's axis is not tilted towards or away, so pretty much from the North Pole all the way down to the South Pole, nearly equal amounts of daylight. Alaska and Texas would be equal on those 2 days a year. And then we have solstices, and these are when Earth's tilt is the most toward or the most away from the sun. It's maximized. Okay, our December winter solstice, again, this is northern hemispheric centric because northern hemisphere is tilted away in December, but the opposite is true for our southern hemispheric friends. They would be tilted towards the sun. So December is actually peak summer for Australia. And then June, our summer solstice in the northern hemisphere. Maximize daylight hours, right? So now we're kind of in August, we're in between June, September now, we're somewhere here in our orbit. Our days are getting shorter and we'll be all the way back over here to our winter solstice pretty soon. What it feels like no time at all. All right. So last question, and then we'll have another short break. Which position would the Earth be in when the South Pole, my favorite place, experiences 24-hour nights? All righty. So we want to know where the southern hemisphere, the South Pole, is tilted away from the sun and where that's maximized. Okay, so we know our angle of tilt here based on the diagram. If we go back here to B, it would look something like this. Okay, A and C are equinoxes. D, in this case D, the southern hemisphere would be tilted towards the sun. So the answer is B. Okay, at B in this diagram and this orientation of the tilt, southern hemisphere would experience 24-hour nights. And that would be the southern hemispheric winter. All right. So I'll leave you on this for a few minutes. Let's go ahead and take a little break, just a short 5-minute break. Let's meet back at 3:23 and we'll continue on. All right. So we'll finish up here for the rest of the day. So I left you with this slide looking at seasons, right? So what matters is which direction the hemisphere you're in is pointing, right? Is it towards the sun? Is it away from the sun? And I'm not a huge fan of this diagram because it has the sun in different orientations, but what matters is when we're looking at diagrams, where is our axis tilted? Towards or away? And that impacts our seasonal heating and cooling. And that is why we have seasons. The fact that it is warmer in what we call summer is because our hemisphere is pointed towards that sun. Okay, so the solar angle or beam spreading concept is it's related to the angle of the sun in the sky. So because our Earth is tilted and our Earth is round, different latitudes are going to experience the sun at a different angle in the sky. And that will also impact how much area the energy from the sun gets spread over. Okay, because if the sun's radiation is coming in at an angle and hitting the surface at an angle, it's going to be spread over a larger area. And that's going back to that concept of holding the paper either completely perpendicular or at an angle. And also you could think of it now as holding the light. Is the sun's energy directly above us, right above our head, or is it coming at an angle into the atmosphere? Okay. And this idea of beam spreading and solar angle explains why the poles, the North Pole and the South Pole, are still colder than the tropics, even when there is more sunlight or daylight hours. It's because the energy is still being spread over a larger distance and it's being dispersed. It's not as hot, even in those 24-hour day times. Okay, so here is, I have two diagrams of our Earth's tilt and different times of the year. Which direction, or excuse me, which diagram correctly shows the way Earth is tilted today? All right. So when we look at our diagrams, we have to look at times, right? So what times are shown here? We have January and July. In diagram A, in January, Northern Hemisphere experiences winter. And so my question is, does the diagram show that? Yes, it does, because the Northern Hemisphere is tilted away from the sun. Okay, and then in July, the Northern Hemisphere is in summer. Right, we just had fun summer stuff in the heat, and we're tilted towards the sun. Okay, now B, the reason I show you B, so the answer is A. A is the answer today. The reason I'm showing you B is that the tilt, the direction of Earth's tilt does change through time. And we're going to talk about that when we talk about why our Earth's climate can change. And if you change that orientation, so now in what we call January, the Northern Hemisphere is pointed towards the sun and closer. That's going to impact temperature. We'll have more extreme seasons if the Earth is tilted that way. Okay, so we'll get to that in a few weeks, but just wanted to give you a sneak peek or a little teaser that our tilt can change, can switch. This graph here, this figure, is showing the trends in shortwave radiation. So how much incoming solar radiation, sometimes referred to as insolation, incoming solar radiation. What do you notice about the trends? And I'll point you to look at the date or the month is shown at the top right. So we're in May, June, July, August, and our colors tell us the shortwave radiation. What do you see? Right. Oops, let's see if I can restart it. If we go back, the peak, the highest number of insolation, incoming solar radiation, is tracking or following the seasons, or the summer season, to be more specific, right? So now we're in August, September, October, excuse me, we're going into Southern Hemisphere. Well, now we're in Northern Hemispheric summer, and then we're going into Southern Hemispheric summer. Okay, and great point is that the equator sees a higher amount of incoming sunlight all the time. Okay, the equator here, right around the tropics, 0 degrees north, or 5 to 10 degrees north-south of the equator, gets a lot of sun all the time. And that is why it's always hot there. Okay, this seasonal change in the equator, in the tropics, is mild. It's muted as compared to, say, Alaska or, South Africa. Okay, so what controls our planet's temperature? We talked about our solar constant, okay? And we also talked a bit about our mechanics, the fact that our orbit is the way it is and that we're tilted. Now we're going to talk about the actual temperature we feel on Earth's surface, because we're going to start to bring in some of our atmospheric properties. Albedo. Albedo is a very important one, and it's one we're going to talk about a lot, because when we change the albedo of our surface or our planet, it has really, really quick implications for climate. So albedo is the percentage of incoming radiation reflected by an object. Okay, so if it's reflected, it's not absorbed. You can either reflect or absorb. That's really the only two things we're going to do with our surface features on our Earth. So here I have box A on the left and box B on the right. You already know about albedo. I'm sure of it, because we've been taught our whole lives what we should and shouldn't wear outside in the sun on a sunny day. Which one of these has a lower albedo? Oops. Well, that's confusing. Thank you. Okay, well, we'll talk about it. So that makes sense as to why we're almost 50-50 here. Okay, so my bad. The surface here that has a lower albedo would reflect less, absorb more. That would be A. Okay, our darker surface is going to reflect less. Okay, now maybe this one will be better. Life is better with cats in general. So which lazy cat here has the higher albedo? Is it Sally or Toad? And these pictures are definitely pre-COVID. These cats have gotten much bigger during COVID. Those little stinkers. Okay, so the answer here is B, okay? Toad here has more lighter colored fur. He has both black and white fur, just like Sally. She has a little bit of white fur on her belly, but Toad has more of that lighter surface and will reflect more incoming sunlight. And that actually is true. I've measured his temperature difference in his darker surface, his fur versus his light fur when he's in the sun. And it's about like 5 degrees difference. Okay, and so you can see how that would play out on Earth's surface. Okay, we're going to skip that. Earth's albedo, or our reflectivity, is not uniform, right? If we look at an image, a satellite image of Earth, we have all of these different colored surfaces, right? We have darker desert, very bright, bright desert. We have bright ice. We have darker forest and pretty dark ocean. When we take all of those surfaces and all of those reflectivities or albedos and average them, weighted average them based on the surface area, we get a number of about 30%, meaning 30% of the incoming sunlight gets reflected because of the brightness or the reflectivity of the surface. Now, my question for you to think about here, does Earth's albedo change? And if so, what timescales are we referring to? Are we thinking about seasonal, yearly, hourly? What do you think? Yeah, okay. Seasonally, for sure, all of them, right? Hourly, it could be something like clouds, right? So clouds are pretty bright, reflective surfaces, and you get storms, you get weather. Certain parts of the world get weather. I know Southern California might not get the most weather, but places like here, like look out the side today, this morning, it was pretty overcast where I'm at. By the way, I'm not in California, I'm in Colorado. And now it's pretty sunny out there. Okay, so our albedo can change, and it's also changing now quite drastically because we're changing the amount of ice on land. Our glaciers, Greenland, Antarctica are changing quickly, and those are very bright surfaces that greatly impact that number. Okay, so you can look at this, you can have your own thought experiment. Today we won't go through it, but we can look at the range, right? When I give you a number for an albedo, it's really an average, because when we look at snow, fresh snow is different than older snow. And so these are the ranges in albedo for different Earth surfaces or clouds, like cumulus, cirrus, stratus. These are all clouds. And then we have sand, ice, different types of sand. Is it dry? Is the soil dry? Is the soil wet? What about our ocean water? Okay, and so we can think about, if we change a lot of snow and ice and replace it with ocean water or dark forest, how that will impact our planetary albedo, and therefore the amount of energy that the Earth is reflecting or absorbing. So real life, what's happening in the recent decades, recent years, this is what we call a melt pond on the surface of Greenland, one of our massive ice sheets on our planet today. Which surface has a lower albedo? All right, so lower albedo means it reflects less. This blue melted ice, now it's water. These melt ponds have a lower albedo, which means they reflect less sunlight and absorb more, which means the water heats up and then melts more of the surface away. And we see this happening in Greenland in the summer and spring a lot now, where we get rapid and large amounts of surface melting in Greenland, okay, because of this relationship, or what we call a feedback, okay? Climate feedback loops are really, really important when we think about how a change in one component of the Earth system could impact another. And you're going to see these a lot in this course. So let's think about what we're talking about. So in our feedbacks, we have the different kind of components, and those are shown by these boxes, right? So we have surface temperature, we have the amount of ice on Earth, and then Earth's albedo. We can kind of consider them individual factors or components of our climate system, Earth system. And we can think about how each one of those components interacts with each other. And we call those couplings. A positive coupling means that an increase in one component leads to an increase in the next component, or a decrease in a decrease. It just means that the sign of the change between the two components is of the same sign. Positive, positive, negative, or negative. Those two components are positively coupled. A negative coupling means that a change in the positive of one of our components leads to a decrease or a negative change in the other, or vice versa. Okay, so when the components are negatively coupled, we see opposite changes in them. Okay, so let's look at it. Surface temperature. If I increase surface temperature, what will that do to the amount of ice on Earth? Just put I for increase or D for decrease. Will that increase I or decrease the amount of ice on Earth? Okay, decrease. So the amount of ice is decreasing. And so if I'm thinking about my two components here, how are they coupled? That is a negative coupling. So I draw that as this arrow with the rounded end. Now, if the amount of ice on Earth has decreased, what does that do to Earth's albedo? Does it I increase it or D decrease? Decrease, okay? The reflectivity of our planet would go down if we remove the ice, the bright surface. Okay, so now these are both negatives, decreases, but they're of the same sign. They're both negative, so that's actually a positive coupling. We get the same change on both of our components here. And then lastly, if Earth's albedo decreases, what happens to Earth's temperature? If we reflect less incoming light, will our temperature I increase or D decrease? Increase, okay? And so we see that this again is a negative coupling because we start, albedo is going down, but temperature is going up. So coupling refers to the arrows between our boxes or components. A positive or negative feedback refers to the whole loop. A positive feedback does not mean good or bad. Okay, so let's pause here. When I say positive or negative, I'm not referring to whether or not it's a good or bad thing. I'm referring to whether or not in a positive feedback, the change is amplified or continues by the time I get back to the initial change. A negative feedback means I've dampened or moderated the initial change by the time I get back. So in my case here, my surface temperature, I started with an increase. All of my Earth components coupled together led me to a positive change, another increase. So would this be considered a positive, P positive, or N negative feedback loop? Okay, this is a positive feedback. Why? Something changes our temperature of our planet. I don't know, maybe it's human activity increasing the amount of carbon in our atmosphere. And so our surface temperatures increase. Then the amount of ice on Earth decreases, impacting our albedo and allowing our temperature to continue to increase. Positive feedback, it amplifies the initial change. Positive feedbacks are hard to get out of because they accelerate. And this is real. This is happening real time. You know, our ice sheets are melting. Our albedo is changing. Okay. So we talked about our albedo. On Thursday, we're going to talk about the next thing, which is our atmosphere. The gases in our atmosphere, the greenhouse gases, maybe you've heard of them, they will impact our planetary temperature. The actual temperature we feel on Earth at the surface, what's in our atmosphere, that's going to play a big role. So we're going to talk about that on Thursday. What I'd like you to do before Thursday is today, I'd like you to complete your check-in. Go to assignments. You'll see lecture 1, daily check-in. Super simple. You might have to look at the syllabus to answer a few questions. Maybe that's my intent. Please also have downloaded homework 1. I'd like you to look through it. You don't have to necessarily start it, but I really would like you to just read through it, see if there's things that you just really don't understand right now. Flag those. We can discuss a little bit if you have questions on Thursday. But please have that downloaded and ready to go because I might have a little time for you on Thursday to look at that together as a class. And then also please look at the final project instructions. I'm going to go through that in more detail on Thursday. I already see some of you have submitted your climate change solutions you'd like to research, which is great. Thank you. But I'll go through that on Thursday. Otherwise, I'll see you Thursday. If you have any lingering questions, I'm going to stay on for a few minutes. Always feel free to email Chris or myself if you do have any questions or concerns. I'll get back to you as soon as I am able. Otherwise, see you Thursday. Bye.